This comes out of section 3.3, Rates of Change in Natural Sciences. To start off, in general, we've got some function y equals f of x, and we're going to, if x changes from one value to another, x1 to x2, delta x, or change in x, is just the difference between those, x2 minus x1. Our delta y then would be the difference between the y values, so y2 minus y1, or in this case, f of x2 minus f of x1. So our rate of change, if we were looking for a slope anywhere on between 2 points on that graph, would be change in y over change in x. Now that we've gotten into calculus a little bit, we can see that if we were looking for an instantaneous rate of change, that we'd be able to take the limit. The limit is that delta x goes to 0. In other words, as those two x coordinates get infinitely close together, of this delta y over delta x, which is essentially what we're talking about as the derivative, right? So the limit as x2 approaches x1 of f of x2 minus f of x1 divided by x2 minus x1. Essentially what we're repeatedly talking about here is the value of the derivative, in this case at x1. So there are lots of things that change in science. If you're talking about chemistry experiments, you've got concentrations of reactants that change. You can do ecology, biology examples where populations change. You can do, physical things where you're looking at, the first example I'll do here is a balloon being inflated, so the volume is changing. So as long as we can have a function that relates one variable to another, we should be able to find a rate of change of one variable with respect to another. So here's our first example. So to simplify our lives a little bit, I've called this a spherical balloon. That way we can use the equation of volume of a sphere instead of trying to figure out the unusual shape that is most normal real balloons. You'll have on your formula sheet that volume equals 4/3 pi r cubed when you're talking about a balloon. Or a sphere, sorry. If I look at the graph of that, as volume and radius, as radius goes up, volume goes up, the negative parts of this graph don't make a lot of sense to even worry about when you're talking about the radius of a balloon and the volume, because you're not going to have a negative radius. And what we're asked for is the rate of change of volume with respect to radius. So we need to take the derivative. I have 3 times 4 over 3 times pi times r squared, which is just 4 pi r squared. Now, in particular, when that is when the radius equals 20, we're going to have dv by dr is going to be 4 times pi times 20 squared. So if you say 20 times 20 is 400, times 4 is 1600, 1600 pi would be a reasonable answer. You could, depending on what the question asked you, if they wanted you to round it off in some way, you could find that it was 5,000 and something, but in this case this is good enough. And our units here are unusual because our volume is in centimeters cubed and our radius is in centimeters. What that unit is saying is that at that instant where radius is at 20, that for every centimeter that you increase the radius, you actually increase the volume by 1600 pi centimeters cubed. So the radius increases a small amount, the volume goes up what seems like a way larger amount, and that's due to that 3 dimensions kind of thing that's going on. So kind of not necessarily a science example in that you do a lot of inflating balloons in biochem or physics in high school, but still an example of one variable changing with respect to another.